As a continuation to our lesson 1.5, we will discuss now the LU factorization. Let us define first the lower and upper triangular matrices. So a square matrix is lower triangular if all the entries above its main diagonal are 0. Also, a square matrix is upper triangular if all the entries below its main diagonal are 0. So to illustrate this, we have these matrices. So this is a lower triangular matrix. Observe that all entries above the main diagonal are 0. And in here, all entries below the main diagonal are 0. So this is a 3 by 3 upper triangular matrix. Next is the definition of LU factorization. If the n by n matrix A can be written as the product of a lower triangular matrix L and an upper triangular matrix U, then L times U, which is equal to A, is an LU factorization of A. For example, this matrix is equal to the product of these two matrices, where this one is a lower triangular matrix and this one is an upper triangular matrix. So this is called an LU factorization of this given matrix. Also, we have another example. So you can check that the product of these two matrices is equal to this one. And this is a lower triangular matrix and this one is an upper triangular matrix. So again, these factors are the LU factorization of this matrix A. Now let us discuss how to find an LU factorization of a given matrix. We begin by reducing A to upper triangular form while keeping track of the elementary matrices used for each row operation. So again, we will reduce this matrix A into an upper triangular form. That is, we want these entries below the main diagonal to be 0. Okay, and then we will keep track of those elementary row operations being used. Okay, so first, we want this to be 0. So we multiply by -2, row 1 by -2, and then we add it to row 3. So we will have this matrix. So we have that. So again, this becomes 0. We multiply this by -2, and then we add it here. So we have -4. We multiply by -2 and add in here. So we have 2. So the elementary row operation we use is 1. Okay, so next is the corresponding elementary matrix. We have, again, we apply this elementary row operation to the 3 by 3 identity matrix. So we will get this corresponding elementary matrix. So let us name that one as E sub 1. Next is, we want this to be 0. Again, we want the entries below the main diagonal to be 0. So to make this 0, we will multiply row 2 by 4, and then we add to row 3. So we will get this matrix. Multiply this by 4, and then we add it here, so that is 14. So the elementary row operation, we have this. And we will apply this to the 3 by 3 identity matrix to get the corresponding elementary matrix. So that is, we have E sub 2. We name it as E sub 2. Now observe that this matrix is already an upper triangular matrix. And let us call it as U, so that we have E sub 2 times E sub 1 times A equals this matrix, which is, we call it as U. And from this, it follows that A is equal to the inverse of E sub 1 times the inverse of E sub 2 times u. Now, to get the inverse of e sub 1, notice that since we can convert e sub 1 back to the identity matrix by multiplying r sub 1 by 2 and then add it to r3, then we have get new r3, then we will have the inverse of e sub 1 as 1 0 0 0 1 0 2 0 1. Okay, so again, we got this from the identity matrix, 3 by 3 identity matrix, and we apply this row operation, elementary row operation. Also, to convert e sub 2 back to the identity matrix, we multiply r2 by -4 and then add to r3. So again, we have r3 plus real new r3. So we apply this to the 3 by 3 identity matrix so that we get the inverse of e sub 2 as 1 0 0 0 1 0 0 -4 1. So moreover, notice that the product of lower triangular matrices e sub 1 inverse, e sub 2 inverse, this 2 is equal to this one, which is a lower triangular matrix. Now let us denote it by L. Therefore, we have now the LU factorization of A. That is, A is equal to the product of 1 0 0 0 1 2 -4 1 and 1 -3 0 0 1 3 0 0 14. So again, this is the lower triangular matrix and we have the upper triangular matrix. Next, we have a remark here. If a row reduces to an upper triangular matrix U using only the row operation of adding a multiple of one row to another row below it, then A has an LU factorization. So your U is equal to the product E sub K is up to E sub 2 times E sub 1 times A. And from this, we get our A as the product of the inverses of these elementary matrices times U, which is therefore we have now the LU factorization because the product of these inverses is equal to a lower triangular matrix. Also, once you have obtained an LU factorization of a matrix A, you can then solve the system of n linear equations in n variables ax equals b very efficiently in 2 steps. So first, you write y equals the upper triangular matrix times the x and solve ly equals b for y, where L is the lower triangular matrix. And then for the second step, you solve for x in the equation ux equals y. Note that the column matrix x is the solution to the system since ax equals lu times x is equal to ly, where your y is equal to u times x, which is equal to b. So for example, we solve the linear system, this linear system. The coefficient matrix of the given linear system is we have 1, -3, 0, 0, 1, 3, and then we have 2, -10, 2. Now let us call this one as A. Actually, this matrix is in the previous example where we got the LU factorization of this matrix as we have 1 0 0 0 1 0 negative 4 1 times 1 negative 3 0 1 3 0 0 14. Okay, so this is the LU factorization of A. Now, following the steps given, let us first let y be equal to ux and solve the system ly, sorry, is for y. So we have the u here, the L rather, we have 1 0 0 0 1 0 to negative 4 1, and then we multiply it by a column matrix y. So we have y sub 1, y sub 2, then y sub 3. Now let us equate it to b, which is from the given system we have negative 1, negative 5, negative 1, negative 20. So let us continue. So from here, we solve for y by forward substitution. So we equate this, we make the linear system of linear equation from here. So we have y sub 1 from here is equal to negative 5. And this multiplied to this, we have y sub 2 equals negative 1. And then the last, we have 2 y sub 1 minus 4 y sub 2 plus y sub 3 equals negative 20. Okay, so we substitute these values in here. So this implies that 2 times negative 5 minus 4 times negative 1 plus y sub 3 equals negative 20. And then simplify this. So we have negative 10 plus 4. So we have negative 6 and then transpose on the other side. So y sub 3 is equal to negative 14. Thus, y, the column matrix y is equal to, again, we have y sub 1, y sub 2, and y sub 3. So we have these values here. So we have negative 5, negative 1, and negative 14. Now let us solve the system. Solve the system U, the upper triangular matrix, x equals y for x. So that is, we use the upper triangular matrix 1, negative 3, 0, 0, 1, 3, and 0, 0, 14. We multiply by the unknown x, so we let that as x sub 1, x sub 2, and x sub 3, which is equal to our y, which is negative 5, negative 1, negative 14. So from here, we get the linear system. We have x sub 1 minus 3, x sub 2 equals negative 5. And then this times this. So that is x sub 2 plus 3x sub 3 equals negative 1. And lastly, we have 14x3 equals negative 14. So we solve this by back substitution. So first, we solve for x sub 3. So x sub 3, this implies that x sub 3 is equal to, divide both sides by 14. So we have negative 1. And then we substitute x sub 3 to the second equation. So x sub 2 plus 3 times negative 1 equals negative 1. So it implies that our x sub 2 is equal to, this is negative 3 transpose on the other side. So that is x sub 2 is equal to 2. And then we substitute these values x sub 2 and x sub 3 to our first equation. Actually, we have just x sub 2. So x sub 1 minus 3 times 2 equals negative 5, which implies x sub 1 is equal to negative 6. So plus 6 there, so that's 1. So therefore, our solution to the system, so the unknown is x, equals x sub 1, which is 1, x sub 2, 2, and then x sub 3, negative 1. Now let us try another example. Let us try to solve this system using the LU factorization. So the coefficient matrix. So we have equals 1, then we have y minus z equals 2. Now let us use x sub 1. Sorry, let us use x sub 1 and then plus x sub 2 equals 1, and then x sub 2 minus x sub 3 equals 2, negative 2 x sub 1 plus x sub 2 plus x sub 3 equals negative 2. Okay, again, let us solve this linear equation using the LU factorization. So first, we get the coefficient matrix corresponding to this linear equation. So let us name that one as A. So we have 2, 1, 0, 0, 1, negative 1, and negative 2, 1, 1. Okay, next is we want to express A as a factor of a lower triangular matrix and upper triangular matrix. So let us do the same steps as we did a while ago. So we list down the matrix that will transform this one into an upper triangular matrix, and then we also include the elementary row operations. This is used to get the corresponding elementary matrices. Okay, so to make this an upper triangular matrix, we want the entries below the main diagonal 0. Okay, so let us start here. So to make this 0, we will add rows 1 and 3. So to do that, and then we add, we have 0, we have 2, and then we have positive 1. Again, what we did is we add rows 1 and 3 to get new row 3. So the corresponding elementary matrix, let us name that as E sub 1. So we apply this to our identity matrix, a 3 by 3 identity matrix. Okay, so add rows 1 and 3. So we have 1, 0. That is to get new R3. So 1, 0, 1. Okay, so that is the elementary matrix first. And the next, we want this to be 0. So we apply we multiply by -2 this row 2, and then we add to row 3. So row 3 plus -2 of R2 to get new R3. That's 2, 1, 0, 0, 1, -1. And then, so this becomes 0 now. Multiply by -2. So that's +2 plus 1. So that becomes 3. So the corresponding elementary matrix, we apply this elementary row operation to the identity matrix. So row 3 plus the negative of, no, we multiply this by -2. So we have 1, 0, 0, 0, 1, 0. We have 0, -2, 1. Okay, so we have now from there, we call this one as our U. So that is E2 times E sub 1 times A is equal to the upper triangular matrix U. So this would imply that A is equal to the inverse of E sub 1 and then the inverse of E sub 2 times U. So we get the inverses of these elementary matrices. So again, what you're going to do is just simply look at the matrix and then find out the elementary row operation that will be used to convert this back to identity matrix and then apply it to the identity matrix so that you can get the inverse. So in here, we can multiply this by -1 and then add to row 3. So what we do is we do that also in the identity matrix. So we have 1, 0, 0, 0, 1, 0, -1, 0, 1. Also, the same way, we can solve for the inverse of E sub 2. So that is 1, 0, 0, 1, 0, and then 0, 2, 1. So we multiply now the inverse of E sub 1 by the inverse of E sub 2. So we have 1, 0, 0, 0, 1, 0, -1, 0, 1 times the inverse of E sub 2, which is equal to, we have 1, we have 0, 0, and then we multiply this in here, so that's 0, and then we have 1, 0, -1, 2, sorry, that's 1. Okay, so we just multiply this third row to each of the columns here. Okay, so you will get this, and this is now our L. So therefore, our LU factorization of A is, so this is our L, and then this is our U. So we have 2, 1, 0. Okay, so this is a lower triangular matrix, and this is an upper triangular matrix. Okay, next, we will follow the two steps that we have discussed. So first is we let ux equals y, and we solve for y in this equation. Okay, so we use the lower triangular matrix first. We have 1, 0, 0, -1, 2, 1. We multiply it by y. So we have y sub 1, y sub 2, and y sub 3, which is equal to our b. We have 1, 2, -2. Okay, then we have We multiply this, so we can create now the system of linear equation. Y, and then y sub 2 equals 2, and then y sub 3, negative y sub 1 plus 2y sub 2 plus y sub 3. So we use these coefficients, we multiply it here, so that is equal to this, that's negative 2. And then by forward substitution, or we use these values of y sub 1 and y sub 2, we substitute in here. So we have negative 1 plus 2 times 2 plus y3 equals negative 2. So this implies that y3 is equal to, this is negative 1 plus 4, so that's positive 3. So you transpose that one, so that's negative 3. So negative 2 minus 3, so that's negative 5. So therefore, our y is equal to 1 to negative 5. Okay? And then next, we solve for ux equals y. Okay, so we have that one. So we now use the upper triangular matrix. We have 2, 1, 0, 0, 1, negative 1, and 0, 0, 3 times x sub 1, x sub 2, and then x sub 3, which is equal to our y, 1 to negative 5. Okay, so we form now the system of linear equation from this, which is equal to 1. Then x sub 2 minus x sub 3 equals 2. And then last we have 3, x sub 3 equals negative 5. So from here, our x sub 3 is equal to negative 5 over 3. We substitute this value to this second equation. So x sub 2 minus negative 5 over 3 equals 2. So that is, this implies that x sub 2 is equal to, this is positive 5 over 3, transpose that one on the other side, so that's negative 5 over 3. So therefore, we have 1/3. And then, we substitute this value to the first equation. So 2x sub 1 plus 1/3 equals 1. So this implies that 2x sub 1 is equal to 2 over 3, which implies that x sub 1, we multiply by 1/2 on both sides. So that is 1/3. Okay, so our solution to the system, given system of equation, x equals 1/3, so that is our x sub 1, and then 1/3 also for x sub 2, and then x sub 3 is negative 5 over 3. Okay, so that's it. That is how you solve for the x in ax equals b using the LU factorization of the coefficient matrix. So that's the end of our chapter 1.